Okay, ladies and gentlemen, good morning. We are live now.
Okay.
Hi, YouTube. Yep, you're on Mr. Myers' live stream. Mr. Myers can actually sustain a voice today and talk a little longer than the last 2 weeks. Yay. Why wouldn't he? All right, ladies and gentlemen, so today's goal, the last lecture for the unit in YouTube Live, just so you had the video available to you. We're going to take a look at buffers, and then we're also going to take a look at acid-base titration, not in the context of doing molarity calculations, but instead looking at titration curves and more of that side of things. So a moment ago before we went live, I alluded to titration with indicator as being more qualitative, which now that I think about it is kind of a lie because we still do molarity calculations, but you're at least visibly, you can see a change take place in the titration. With titration curves and potentiometric titration, we're going to be utilizing probes and graphically measuring or attaining data and graphically measuring and seeing what the titration curve looks like to do our analysis that way. But again, today, buffers and titration curves. So a buffer system up here, a buffer system is a two-component system that prevents major change in pH. So the idea here is that your buffer system is made up of either a weak acid and its conjugate base. For example, so put 1 and 2. So for example, a weak acid and conjugate base might be acetic acid and acetate, which would be in the form of sodium acetate, but sodium is a spectator ion, so it really doesn't matter if we write it out. And then the other option for a buffer is a weak base and its conjugate acid, which really could be this, but flipped around. Or maybe we're more familiar with something like ammonia and ammonium. Okay. And I can already hear someone watching the live stream in class. Way to go, guys. What?
So instead of the slash, would it be a plus mark or like what is it? I'm confused about the slash.
It's nothing intentional there. Just it's two things. It's not dividing.
Okay.
It's
so
just
like gas and plus.
Okay. So put a plus sign there and there. Do what you need to do. All right, so this buffer is a two-component system. By two-component, we're saying weak acid and conjugate base, conjugate acid, and the goal is that if we add any small amount of strong acid or strong base, then it's going to be converted in the presence of the buffer to the weaker acid or base. Okay, so if you have a system in place, you add something strong, it's going to be converted to weak, and so the overall effect is minimized. So here on the left is a sample buffer system where we're using acetic acid and acetate. Okay, acetic acid is a weak acid, acetate is a weak base. We're assuming that it's probably sodium acetate that we're using, but again, that sodium ion is a spectator ion and is not going to be playing a role. Right, much like most spectators at a sporting event, if we ignore the idea of the 6th man or the 12th man or person, then the spectator has no outcome on the game being played. Just like in these buffer systems, the spectator ion is there because that's how we balance charge to introduce the substance. But reactivity-wise, it's going to have no role. It's just a spectator. It's just there hanging out watching. Okay, so let's say we have a buffer system and we add a strong acid like HCl. Is the HCl going to combine with the weak acid or the weak base? probably the weak base, right? Acid and base. So if we combine it with the weak base, again, sodium, if sodium is a spectator ion, it's going to be hanging out with chloride. But the goal, or the thing here, if you notice, we have a strong acid with HCl, and it gets converted to the weak acid in the process. So strong acid gets converted to a weak acid. On the flip side, if we use sodium hydroxide as a strong base, the strong base is going to combine with the weak acid, and it's going to make the sodium acetate, which is already in solution, as the weak base. So here we take sodium hydroxide, and it's going to be converted into the weak base sodium acetate. Okay, so that goes back to our definition of a buffer or description where the strong is always converted to the weak. So strong acid to weak acid, or strong base to weak base. And by doing so, even though having a strong acid or strong base could greatly affect the pH of a system, by putting it into a buffer, you convert it to something that's already in the buffer system, so you're not really changing the pH. Okay. If anything, if you go into IB chemistry, you might look at this with something called Henderson-Hasselbalch. And the Henderson-Hasselbalch equation is something like, what is it? pH equals pKa plus what is it? Log. I think I just messed up my equation, but basically I'm going to ignore this so you don't see it here. But it involves a comparison of pKa as well as the different buffer components, their concentrations. So you have the Ka of the weak acid, combine that with concentrations of the acid and its conjugate base, and then you get the pH. So you're not going to have a huge effect on pH at the end. And we're not going to do the math in here. If you do IB Chem, I would imagine that you would see it. I know when I've taught AP Chem in the past in Indiana that Henderson-Hasselbalch was something that was used when we had this discussion, but it's not at this level. Okay, so just keep in mind, strong converted to weak, strong converted to weak. So some importance of buffer systems. These are just really some fun facts. Living organisms, if you think about our blood is balanced at a certain pH. It's not 7, it's not neutral. I think it's like 7.4 maybe. But the idea is that if we, our blood is balanced or we have other buffer systems in place, that if we add too much acid, you could undergo acidosis, or you could undergo alkosis, which would be too much basic or too much base present. So significant pH change can lead to illness or death. Emily?
Is there such a thing? I know like the pH scale is a logarithmic scale, but does a neutral base or just a neutral substance have to be like exactly 7 or pretty close to the 7.4 like so? I guess if everything's... If
it's 7.4, it would be considered basic. It's okay. Near neutral, but it's basic. But that's at a certain pH. It's 7.4, I think. I might be mistaken on the exact pH. But the idea is if you introduce something to the bloodstream that affects that pH, then you could undergo illness or death or certain conditions that affect you.
Got it. Thank you.
Ladies and gentlemen. Okay, another place where we see buffer systems would be seawater. So if we look at marine life and those ecosystems, the water is going to have a certain pH, and so the fishes and algae and plant life will be able to sustain themselves at that plant or at that pH. And if you change the pH, like make it more acidic, things die. Okay, there's an example with salt hydrolysis. If we looked, there's some copper mines that I've seen pictures of where there's like streams or rivers nearby, and the copper sulfate or the copper salts that's in the mine will leach out into the water or through the groundwater, and it turns the river teal, just like the color of our copper salts. Yeah, it looks neat, but then they test the pH, and the pH is like -3 because it's sulfuric acid is the parent acid for that type deal, for the copper sulfate salts. And so fish can't be sustained at a -3 pH.
So it's effectively death water.
Yeah.
Oh.
So see if I can find a picture here.
Dude, why gotta be like that?
It's a joke.
Unnecessary.
Dude.
So you go, here's a picture of it where this was considered a mining disaster, and so a lot of the material seeped out into the water, and you can see the significant color change. And there's not going to be, obviously it's very rocky too, but it's not going to have much plant life in there. You also get some other places like this, for example, where there's a copper mine that had a spill or release of copper, and so it turned the water a different color. The pH is going to be affected, and the fishies are going to die. Okay. Okay, and then other things like products for human consumption. A lot of your foods are going to have buffers built in. For example, citric acid and sodium citrate together. So you have the acid, which is a little sour tasting, and the sodium citrate will help to balance that in terms of pH. Or phosphoric acid and sodium phosphate. You guys know like Coca-Cola has phosphoric acid in it?
No.
Isn't it to keep the sugar down? It also had Coke in it
For a while, maybe. Yep. I remember uses of phosphoric acid. How many of you have had braces?
Not me. Had what?
Braces.
Oh, no.
So when I was in high school, I had braces, and ladies and gentlemen, come on. So when I got braces in high school, in order to clean the teeth, they had to apply a phosphoric acid paste to them, and I had to keep my mouth open. They're like, don't lick, it's phosphoric acid. But the idea, even though it's a weak acid, it was still pretty concentrated. And what it did is it is strong enough to etch the enamel. Teeth cleans them, but provides a good surface for for adhesion. So when they go to glue the brackets on, it's a clean etched surface, and the glue has something to stick to. Okay, much like if you're ever doing any woodworking or something and you want to glue boards together, you might want to like loosely or roughly sand something so that the glue has something to adhere to. It's not necessary, especially if you're doing big glue ups like cutting boards or tables. You actually want the edges to be smooth. But there's some cases, or even if you're applying paint to something, it's a good idea to rough it up before you paint it so the paint has something to stick to. Okay. Anyway, back to buffers. There's some importance of the different buffer systems. Okay. So to review, the basis of buffer action is to establish an equilibrium between the weak acid and its conjugate base, or vice versa. So you have a system, you have both in place, and then if you add the strong acid or the strong base, it's going to react accordingly, and the pH change will be minimized. All right, let's take a look at titration. Okay, so acid-base titration This is, as we recall from before, where we use a solution of known concentration to determine the concentration of a solution of unknown concentration. What we've done before and what you'll do with your lab exam next week is to do it with an indicator. For us, we've used phenolphthalein, which changes pink or magenta when it's basic, and the pH for that has to be, I believe, around 9 for that to take place. So that's one way that we could do titration, using an indicator. Another way is with a pH probe. And by doing this with a pH probe, what we end up looking for is the equivalence point, which I will define in a moment. But the idea of the equivalence point essentially is when like the moles of acid and base are equal. Okay, so equivalence and equal. So I have some more things I'm going to share with you on separate paper to define this. The idea of this midpoint of spike zone, I'll show you what that looks like along with some examples of what we call titration curves. This part here with the pH probe, the technical aspect of this we call potentiometric titration. We're going to take a pH probe and we have these LabQuest minis here, okay, and it's got a plug that's USB. Anyone else has a USB input? Your Chromebooks. So we're going to hook it up to the Chromebook, and then we'll have the probes coming out one of these ends. And the pH probe is going to go in your Erlenmeyer flask while you're doing the titration. And so we're going to do the titration like we would before, where we're swirling. But rather than look for a color change with indicator, we're going to look at the graph on the Chromebook in real time, curve or graph looks like. And that's going to help us determine this thing called an equivalence point. Okay? So we're going to take a look at that next week. Okay. So titration curve. Gentlemen. Guys.
Yeah.
What are you guys doing?
I don't really know. I'm just going to pay attention.
So titration curve, before we look at titration curve and define some things with it, when we've used indicator in the past, and we've seen the indicator changes color, this was indicated as the endpoint of the titration. Okay, so the endpoint is when you have that color change present. Okay. Ideally, color change would happen when the acid and base are mixed in an exact equation proportion. Okay, so ideally the color change, the endpoint, is going to happen when the acid and base are mixed in exact equation proportion. This is called the equivalence point. Okay. For example, let's say you have sodium hydroxide that's aqueous and aqueous hydrochloric acid. The products of this neutralization are what? Generically speaking, the products of a neutralization are
NaCl and H2O.
And what do we call NaCl in its generic sense? Salt. So salt and water. Okay. So ideally, if we have 1 molar NaOH and 1 molar, what we see is that we have a 1-to-1 equation proportion, or a 1-to-1 relationship. So if liters of sodium hydroxide are used, then we would expect 25 milliliters of HCl needed to reach that equivalence point. You see that those things are neutralized into sodium chloride with a pH of 7. Okay.
What is the ISB?
1 molar. Sorry. Okay. So it's just saying, hey, it's like a 1-to-1. So if we have 25 milliliters of sodium hydroxide used in the burette, then we would expect that it would take 25 milliliters of acid to correspond to that. Okay. Unfortunately, or fortunately, depending on how you look at it, not every sample is ideal. This one is, because it's a 1-to-1 situation. You have a strong acid and a strong base. Okay. So an example where we have something that's not ideal. Let's take a weak base like ammonia and a strong acid like hydrochloric acid. And the result is going to be ammonium chloride, aqueous, so there's some water around still. Because ammonia is a weak base and hydrochloric acid is a strong acid, we would expect our salt, or our product, slightly acidic. Okay, so that means our equivalence point is going to happen at a pH less than 7. Okay, so it's saying if 25 milliliters of ammonia, then 25 milliliters of HCl will be needed to reach the equivalence point. But because one's weak and one's acidic, our final equivalent, our equivalence point, is going to be less than 7. It's going to be acidic.
So is the reason why they stick together and like it doesn't go NH4 and Cl because HCl is really strong?
Well, this is ionic, so it'd be NH4 plus and Cl minus. So it's neutralization. We can still write water over here. I didn't because these are aqueous, so it's in the presence of water.
I meant like why they bonded together and why wouldn't HCl just give the proton?
So based on, well, it would. I mean, it'd be NH4 plus and Cl minus, but you have the positive and negative, so they still go together. I just wrote it as the ionic formula. Okay. Similarly, let's say we have sodium hydroxide, which is aqueous, and acetic acid, which is aqueous. The products are going to be sodium acetate, salt, and water. Okay. Notice in this example, sodium hydroxide is a strong base, and acetic acid is a weak acid. So the salt, the product, is going to be what? Slightly basic or slightly acidic? Slightly basic. So we would expect to be at an equivalence point where the pH is greater than 7. Might not be by a lot, but it's still going to be significant enough.
The equivalence point changes based on how strong your acid or base is that's being mixed with the acid or base.
Mm-hmm.
What would happen if, so if they were like both a strong acid and a strong base, it would just be like 7, right?
Yeah.
Okay. What if it was just a weak base and a weak acid?
I have pictures to show you of that. It would, if they're both weak, the equivalence point we'll see is about 7.
Okay.
Because they're both weak, but the point of inflection on the graph we're going to see is going to be hard to pinpoint because they are both weak.
If they're both weak, would you want us to find the strength of them and see which is like which way it kind of falls? Or would it be
I think I just want you guys to look at the graphs qualitatively and discern from there what we would expect. There's not going to be much math in terms of figuring out what the exact one is if it's weak. Okay. So let's look at something called pH curves. On your slides, they have 4 examples of sample graphs. We're going to look at those now. So to do this, we're going to assume equal concentration is 1 molar.
We don't have these.
Yeah, that's why he's rating it.
I don't know the graphs.
That's why I'm writing it out.
Wow. Amazing.
What you have on your graph or on your slides is this, sample graphs. But I'm going to draw them. So for the potentiometric titration, one solution is going to be in the flask, and that's going to be about 25 milliliters, we're assuming. And then the other is going to be in the burette. Again, if they're both 1 molar, I think we're going to assume that's going to take 25 milliliters for both substances to get enough data. But the graphs are going to look different based on if our acid and base is strong or weak. So let's say that we have a strong acid with a strong base. Okay, so we have sodium hydroxide, hydrochloric acid, making sodium chloride, and water. So let's do this from the point of view of adding acid into base. Okay, our y-axis is going to be pH. And our x-axis is the volume of acid added. So the way our graph is going to look, because we're adding acid into base, we have our volumetric flask here. Base is already present in the flask. So if we have a strong base in our, we're going to be starting out at a pH of 14. And as we add acid, it's going to be a sudden drop. And look something like this. Okay, so right around that 25 milliliters of acid is when we're going to have that sudden pH drop. And then adding even a tenth of a milliliter is going to make it fully acidic. So this right here is what we call the equivalence point. Okay, so we expect it to be right around 25. Looks like I'm a little off on my drawing, so there, I moved it a tad. So right in the middle there, at that inflection point where it's going from a negative slope to I guess they're both negative, but the value is going to change right around here. Okay. Let's say, for example, we switch this so it's base into acid. Okay, which is what it's typically going to be, where we have the base in the burette and the acid in the flask. So in this example, we see the volume of base added right around that 25 milliliters. We reach our equivalence point right about there. Which, if you're noticing or catching on, is around the halfway point. So where we have the sharp change here, the halfway point, is where our equivalence point lies. Okay. Now, in case we have a strong acid and a weak base, where do you think the equivalence point is going to lie in this example? At 7, below 7, above 7?
Below 7.
Below 7. Okay. So we're going to assume base into acid again. And because we're starting at a strong acid, we are going to be starting down at pH of 0. And we end up with something like this. Okay. The equivalence point, that halfway point, is at a pH that's below 7. So that would match our hypothesis or our prediction that the pH or the equivalence point should be less than 7 because we have a strong acid and a weak base, so it's slightly acidic. Okay, and in this example would be where we had our ammonia plus hydrochloric acid forming ammonium chloride, which is in water. So weak base, strong acid, we expect the pH at the equivalence point to be less than 7. Okay, we have 2 more examples here. For this one, we'll look at a weak acid with a strong base. Here we're going to look at acetic acid and sodium hydroxide. Forming sodium acetate and water. Okay. By the way, acetic acid is also written like that. Okay, so just some different ways to write it out. So here we're going to assume base into acid again, which is the more typical approach. So pH on the y-axis. And so what we would experience here, we are going to start at, actually, acetic acid is not a strong acid, so we're not starting at pH of 0, but we're starting somewhere around like here. And it's going to look a little more like this. And so notice the equivalence point, the inflection is about here. And so in this case, because it's a strong base and a weak acid, the pH at the end, or the equivalence, is going to be greater than 7. Okay, so do the graphs make any sense with you guys as far as what we're saying our predictions are?
Yes.
For the strong acid and weak base one, like I understand where the equivalence point is, but why is it like going up? Because why would it become like more basic?
Like this one?
Yeah.
Well, it's still kind of going up, but eventually I guess it levels off. And notice it's not actually going up to 14. So it's still basic, but it's not a strong base, so it's not a high pH. Okay. So to kind of review so far before we look at the last one, we have this picture of a flask. Okay, we're assuming the typical approach. You know, our typical approach, I guess, would be looking at this where we have the acid in the flask. You're going to have the pH probe that's going to be in there that's tied to the lab quest in your Chromebook. So like in this case with the strong acid and base, initially our strong acid is such a low pH, we're down here. And then through the burette, we're going to add some of that base dropwise. And as it does it, as we add each milliliter, we'll see that the pH slowly increases because we're starting to become less acidic. And eventually we reach a point where it goes, it shoots right up in pH. And that's the difference. I mean, we're really is probably within a difference of a couple drops where it's going to be extremely acidic to extremely basic. And that's a extreme example because both are strong. But as we're adding the base, we get to a point where they're equal in concentration and equal in the amount that's in there. And then as we add more base, well, then we become more basic than acidic. In this example with the strong acid and the weak base, we started at a really low pH because it was strong acid. And as we add, like we saw with the drawing up here, as we add base into the acid, it's going to become less acidic. Eventually it's going to shoot up and become basic. Okay? But when it's a strong acid and a weak base, the equivalence point is less than 7. Okay? Because we're still primarily acidic. And then here we had a weak acid and a strong base. So it looks a lot funkier because we're starting at a higher pH than we initially did before. It's a lot easier to make it basic. In fact, we probably hit that change, that inflection is probably greater than 7 or close to it. And so this here, we call this the equivalence point. We also call that our inflection, where we're going from being acidic to basic in that sense. Okay, and we finish up close to pH of 14 because it's a strong base.
So is inflection when it like goes either above 7 or below 7?
The inflection is where we switch, like right here at our equivalence point.
Okay.
So we're going from acidic to the base part. Okay. Our last example for today in the last minute and a half is what happens if we have a weak acid and a weak base. We're going to assume a base into acid again. In this example, let's say we have acetic acid with ammonia. And we'll make the salt ammonium acetate. Assuming there's water there too. So in this case, we're going to start with a weak acid less than 7. And we get something kind of like this, where the equivalence point is here, but it's kind of hard to pinpoint exactly where that inflection is because both are weak. So point of inflection, hard to see. Okay, and that's our volume of base added. Okay, and that's all I got for today.
Bye.
We'll see you tomorrow.
Like, comment, subscribe. We have that like button. What is this?